So, ladies and gentlemen, welcome back. Let us continue with part 3 of our basic course to learn some fundamentals on human decision making. Okay, so the overview. So we are now at part 3, human decision making and AI decision support. The agenda for now, so we will do some reflection, follow up from last lecture first. Then we will deal with medical action. Then ask the question, can AI help doctors to make better decisions? We'll learn a little bit about human information processing, and this will lead us to probabilistic decision theory. And then we give some examples where you can look it on your own. Okay, we conclude with the conclusion. Okay, reflection. So I show you an image and you tell me what you see. So the first image is here, number 1. Yes, this is medical text. This is unstructured information. So this is a good example for non-standardized data. The problem here is that it is full of special words, a language mix, abbreviations, error, and so on, and that is still the standard communication for the medical area, so text is very important. Next image. Yes, this is the official logo of the Health Level 7. This is an international standard for transfer of clinical data in medical information systems, and this is called after the OC, this is the 7-level model, and therefore it is called HL7, Health Level 7. Next image, what can you see here? Yes, this is an old class constructor. This is the Union. Union, easy to remember in German, unten offen. This is a collection of sets. And if the set is all distinct elements in the collection, so this is more or less the equivalent of a logical disjunction. Yes, this is well known. This is ICD-11. So this is the International Classification of Diseases, diagnostic tool for epidemiology, health management, clinical purposes maintained by the World Health Organization. What do you see here? Yeah, this is a good SNOMED example. This is the example for hypertension. So A is increasing, B is decreasing blood pressure, so both hypertension. And this is a beautiful example of an ontology as a formal naming and definition of types, properties, and interrelationships of entities that really or fundamentally exist for a particular domain of discourse. So here, for example, in this hypertension. What do you see here? Number 6. So this is an example for a mesh hierarchy for the heading hypertension again. So this is the same example, and it looks like a mesh description database of the NLM. So what do you see here? Yeah, this is typical graph data. So graph is the mathematical term, and technically we speak of a network. So here it is a protein-protein network. Proteins act always in large compounds organized in graphs, building these famous protein-protein interaction structures. This interaction, by the way, make up the so-called interactomics of the organism, and these abnormal BPIs are the basis for diseases. So, for example, Creutzfeldt-Jakob, Alzheimer, and so on, and may also lead to cancer. So this is a very important data type, graph. A last image of our reflection. Yes, this is a good example for the curse of dimensionality. One dimension, so we see here, one dimension here. This data is transformed into 2 dimension, and this data is transformed into 3 dimension. Then you see the data becomes sparse, and this sparsity becomes exponentially worse as the dimension increases. And please remember, this is 1, 2, 3-dimensional. We have problems in depicting or visualizing higher dimensional spaces on this flat surface. But the real interesting data is very complex, meaning it is of very high dimensions. Okay, ladies and gentlemen, then we start with the lecture. So decision making. So decision making is to select the best possible alternative on values, preferences, beliefs, previous knowledge, but also intuition of the decision maker. So you. So every decision making process produces a final choice, which usually prompts an action. So in summary, medical action is medical decision making. So you have a search task in an arbitrarily high dimensional space. The problem here is that we always are limited in time, and this will be shown in the next slide. So you see, decision making can be seen as a problem solving activity limited by time. So the goal is to find an optimal solution to the given context from this arbitrarily large search space, and the problem is the limitation in time. So you see, it is usually, this is according to the famous Gigerenzer study, how much time does a average doctor have to make a decision. So this is this less of 5 minutes. And of course, it depends on the area. So in emergency, it can be even less time. And in the laboratory or at the bench, it can be more time, but also not unlimited. So decision making in German, Entscheidung, Decision, Entscheidung. So this is a cognitive process resulting in the selection of the best of several alternatives. So every decision-making process produces a final choice, and the output can then be an action or an opinion. In this image, we see, this is actually a very old slide from 2008. So this shows a typical clinical decision-making process supported by the so-called second opinion during a project of the Cognitive Engineering Research Group at the Center, or the Scottish Centre for Telehealth. So this is in the early days of telehealth. So, what are the roots of medical decision making? Remember what we have learned in the first part of the course. It is amazing how this now fits together with the roots of medical decision making, and remarkable that it all starts with Hippocrates. So more than 2000 years ago, he spoke about the probabilistic nature of medicine. So a medical record should accurately reflect the course of a disease, and a medical record should indicate the probable cause of a disease. So very, very interesting probabilistic nature of medicine, and cause and effect. And in 1819, then it starts with William Osler, which is regarded as the father of modern Western medicine. And he said, or he stated, medicine is a science of uncertainty and an art of probabilistic decision making. And this more than 100 years ago. And this is really remarkable that this is exactly what current AI, machine learning, is tackling. Prediction models are based on data features. Patient health status is modeled as high-dimensional feature vectors. So this is really very, very interesting. So where are decision trees coming from? So this is the oldest decision support tool. So this is really very interesting. These old decision trees are already used in ancient Greek. Here a very neatly demonstration of it. It is a physician treating a patient approximately 480 BC before Christ. And yeah, what is this? This is a decision tree. So at every decision tree node, you make a certain decision with a certain probability and a utility. And exactly this is very interesting for us. And we have learned this in the previous core lectures, probability and utility. And we will learn about that in this part. So of course, there is always, as I have mentioned, this complexity issue. So decision trees can be huge. We speak about decision forests even. So they can be very huge and they can be very, very complex, so far away from human understandable. But one of the very recent approaches in the field of explainable AI is called interpretable AI, and they are trying to reduce this huge decision forests into smaller decision trees, which is really a very, very complex task. Here, a typical work, this is from Omar Sagi and Lara Roca from 2020. So this is an algorithm which generates a decision tree using an existing decision forest. The danger here, of course, and this is cutting state of the art, and this is an unsolved problem, is how to ensure that you don't lose information. So this is very, very important. Yeah, and here decision tree state of the art in 2020 for this COVID-19 pandemic. So this has the pandemic has resulted in an increased demand for testing, for diagnostic, for treatment, and the reverse transcription of polymerase chain reaction, as seen here, is the definite test for the diagnosis of COVID-19. And X-ray radiography is also a fast and affordable test that identifies a possible related pneumonia. And here in this study, the authors investigate, and this is very recent work from a couple of months ago. So they proposed classifier, and they comprise this classifier as binary decision trees. And each tree is trained by a deep learning model, as we have seen in part 1. And they used a convolutional neural network based on this PyTorch frame. And the first decision tree classifies the images as normal or abnormal. And the second decision tree identifies the abnormal images that contain signs of, for example, tuberculosis, whereas the third does then the same for COVID-19, for these signs. Yeah? And the accuracies of the first and the second decision trees are 98 and 80%. Respectively. This is really relatively good, and the average accuracy of the third decision tree is nearly 95%. So this is really a good example for cutting-edge artificial intelligence for medicine, and based on our basics which we learn in this course. So how to ensure quality measures? This is via guidelines. So guidelines have to be formalized. They are transformed from natural language to a logical algorithm. You know already what an algorithm is, and implemented in a computer, for example, in a computer program or in a decision support system. And they use the algorithm to program this decision support software, which is then used in practice. So work on this formalization has focused on narrative guidelines, which describe a process of care with branching decisions unfolding over time. So these are systematic guidelines, and they have the potential to improve the quality of patient care. But I think you are familiar with this kind of quality measures already. So this is an example. So most work in developing computer interpretable guidelines has focused on the very difficult problem of formalizing this time-oriented structure of guidelines. And this is a work proposed in 2011 by Medlock. They proposed the logical elements rule method. This is called LERM. And although presented linearly in text, in practice, some steps may be done in parallel, as shown in this slide also. And some steps, such as extracting data elements or checking for conflicts between rules, may need to be repeated with the results of later steps as input. Okay, let's go to a more classical example. So this is actually much older. So Reeder and Felsen did in the 1980s a really awesome work about gamuts. So gamut, the word gamut is defined as the whole range of anything. So it indicates a complete list of causes of a particular Röntgen finding or pattern. And most radiologists use this gamut approach without calling it that. It is a gamut approach. So, for example, here you just state the most common and the most uncommon. So you look at an image, for example, at the radiological image, and then you state the most common and the most uncommon diagnosis. And we will look in more detail in the next slide. So here, this is online available, so you can play around with that. So this is, for example, erosive gastritis. So you have common, this is the most common diagnosis and the most uncommon diagnosis. So this is based purely on probabilistic and probabilistic reasoning, as we have in the focus of this course. So what is the simplest decision support process? Of course, this is this was developed in early World War I already. So this is this international triage tags, and this provides for first responder and rescue personnel a standard tagging mechanism, so to quickly decide. And this is the simplest decision support process, and determining the priority of patients' treatment based on the severity of their conditions. So a more elaborate system is this example for a clinical decision support system from relatively old. This is 2006, but it is a really nice example for an integrated framework. So this is practically a good overview of such an unifying framework demonstrating the steps in clinical decision-making process. This framework is patient-centered, meaning that the patient is in the center here. And you have this hypothesis-oriented algorithm for clinicians' approach. So for each step, you have different algorithms, and each step is supported by data and by algorithms to get the best possible decision support in this setting. So an example for prediction models. So this is actually a nice demonstration that many features contribute to a decision. So you have not only one feature, but many features. So for example, from this unstructured information, so this non-standardized data, then you have this, for example, the text analytics part, or the events, the diagnosis, coded diagnosis, procedures, the drugs, the genomic, and all this contributes to this feature. And this can be a very large patient feature vector. And this can then be organized, and this can then be processed by a computer. Because always remember that the computer can only deal with numbers. Okay, can AI help doctors to make better decisions? The answer is surely and obvious, of course. Computers have a huge advantage. They do not get tired, although they are biased as well, because logically we would now say they are not biased, but computers are also biased, but we will discuss this in the further progress of this course. So what are the two types of decisions? This is the basic in decision making. So we have a closer look. So you have type 1 decisions. These are related to the diagnosis. That means computers are used to assist in diagnosing a disease on the basis of individual patient data. Typical questions include, what is the probability that this patient has a myocardial infarction on the basis of the given data, patient history, ECG, and so on. And what is the probability that this patient has acute appendicitis given the signs and symptoms concerning this abdominal pain? This is contrasted to the type 2 decisions, so related to the therapy. For example, computers are used to select the best therapy on the basis of clinical evidence. Examples: what is the best therapy for patients of age X and risk Y if an obstruction of more than 7% is seen in the left coronary artery, as a typical example? Or, next example, what amount of insulin should be prescribed for a patient during the next 5 days, given the blood sugar levels and the amount of insulin taken during the recent weeks? So this is the typical two types of decisions: diagnosis and therapy. So example, a good example, knee surgery of a soccer player. This is a classical problem. And you have these uncertainties. For example, you have these risks, infection in surgery, and they lose the risk of losing mobility, which is dramatic for the soccer player, of course. And this can be treated by our decision trees. So, and you remember, this is a typical decision tree with probabilities. So here, for example, the death is relatively low risk, but you have a relative risk for this poor mobility. And then you have to make a decision with these figures in mind. So this is then the decision support now. This is the clear demonstration for these risks versus success. So, and this goes back to the expectation maximization strategy, which we will discuss in the slide after next. So this is just a further example for a clinical decision tree. So just that you see that this is state of the art still. So again, trees and particular forests can rapidly become very complex, and the big challenge is in making this tree understandable. This is easy understandable for us, but the world outside is much more complicated. So this is the interesting principles. This is the basic. Humans select the action which maximizes the expected utility. So they select an action which maximizes the expected utility, meaning in decision theory, this was found by Neumann and Morgenstern. So this utility theorem shows that, and under certain axiom of rational behavior, so we are talking about rational behavior, a decision maker is faced with risky, we call this probabilistic outcomes of different choices, and they will behave as if he or she is maximizing the expected value of some function defined over the potential outcomes of some specified point in the future. And this is known as the Neumann-Morgenstern utility function. And you have here the two guys here, Oscar and Morgenstern, this is the expected utility hypothesis. So it is a maximization problem. So the same as we have seen in the first course where we talked about the minimization problem. This is a maximization, so an optimization problem where the goal is to maximize the outcome, so to maximize the possible utility out of this. Yeah, and this is also state-of-the-art, cutting edge, so that you see that is a very recent paper a couple of weeks ago. So in this paper, a utility-based multi-criteria model was proposed to support the physicians to deal with an important medical decision, the screening decision problem given during this COVID-19 pandemic. And since this COVID-19 emerged, the number of patients with an acute respiratory failure has increased in all health units throughout the world. And this chaotic situation has led to a deficiency in health resources, as we all know. And this paper, actually this study, used the concepts of multi-attribute utility theory. This goes back actually to exactly what I have shown before. And this puts forward this mathematical model to aid the physicians in the screening decision problem. The model is used to generate which of the alternatives, here you see the alternatives, so we have the three alternatives: ICQ stay, hospital stay, or isolation at home. So this is the decision problem. And here now, this model is used to help which of the three alternatives is the best one for the particular patient with suspected COVID-19 symptoms. And this decision information system is called a site diagram, and this is constructed and illustrated to operate the mathematical model which we have seen before. So this is a good example for multi-criteria decision-making model. So next is the question, what are now the classic decision support models? So here we have an overview about the decision models. So we can first discriminate between quantitative, more statistical models, and qualitative, more heuristic models. And then we have here supervised models, unsupervised model, and neural networks as a crude distinction, then Bayesian, fuzzy sets, and logistic to make a crude discrimination. And then we have these truth tables on the heuristic part, or the Boolean logic can be used, decision trees as we have seen before. Then one method is this non-parametric partitioning, then reasoning models and expert systems and critical systems. We will hear about this later on. So now let's continue with looking more on the human part, so how humans process information. So this is essential to understand decision making. So what are the pressing open questions that you see? What is state of the art? So remember, we have defined knowledge as a set of expectations, and now we have some hard problems of human cognition. For example, the first is, how does abstract knowledge guide learning and inference from sparse data? We have heard about this already. So approximate Bayesian inference in probabilistic models is one answer, and what are the forms and contents of that knowledge is the next question. So probability is defined over a range of structured representations, for example, as we have seen before, graphs, trees, for example, or grammars, predicate logic, schemas, and. And how is that knowledge itself acquired? So by hierarchical Bayesian models with inference at multiple levels of abstraction. This is the so-called learning to learn. And this can deduce to learning as an hierarchical Bayesian program induction. The central question remains open. How does our mind get so much out of so little? I have to remind you that we are all our super examples, exciting medical AI success examples, are working with large amounts of data. So we are talking about big data, and you have seen the problems with little data, and interestingly, the human can deal with little data. Yes, and we don't know why they can do that. So this is the open question. How do humans generalize from few examples? So, for example, sometimes, not always, humans are able to understand the context. So this understanding, no computer on this planet can understand the context. Then to make inferences from little, even from noisy and even from incomplete data sets. There are several studies which beautifully demonstrate that you can do that. Then to learn relevant, and I emphasize here, and I have underlined therefore relevant. So what is relevant? This is really an important question. and to find this shared underlying explanatory factor. So this explaining, this is very, very important, and this is also not inherent in even the best current AI systems. And this leads us in particular between the P of x and the P of y given x, with the causal link between y to x. So this is really this y mapped to x. This is the causal link, and this is a very, very important and difficult question, and this cannot be done by machines so far. So I emphasize again, humans can far not always explain everything, and one human to the other cannot explain. And of course, humans are unpredictable in time as well, but sometimes the humans are able to do so, and we have no idea how they do so. So, an experiment, with this nice experiment presented by the Tenenbaum group from MIT, it will become very clear how our human mind works and what we need for future AI. So, we are learning here about medical AI, and I think this is very relevant that you know about the limitations and of current AI and what we need for future AI. Look please on this slide and look at these nice pure fantasy objects. And now I give you an arbitrarily chosen object, and I select one and give it a name, for example this one, and say this is a quaxel, okay? And then we see this is a quaxel and this is a quaxel, okay? So this is just a pure definition, and you are now able to build rich models of the world, and you can make strong generalizations from alone of these few input data, which is sparse, which is noisy, which is ambiguous. But you can now identify other quaxels as well. So if we look down, there are some other quaxels as well, here and here. So you have learned the concept of a quaxel in a fraction of a second. And this is still state of the art in context understanding. So the human mind makes empirical inferences that go far beyond the data available. And this is a beautiful work by Tenenbaum et al. From MIT. And one of the main questions remaining here is, how does abstract knowledge guide learning and reasoning from few data? And a further question is, what forms does our knowledge take across different modalities? So this is what interests us in research. And this leads exactly to this necessity of multimodal explainability, which I have already mentioned several times during this course, because in the medical domain, many factors contribute to a result. And we are interested in the counterfactuals. What happens if you take away an input data from your result, okay? And this brings us to interpretable models versus interpreting models. But now we will continue and look at one of the unsolved problems in human concept learning. So this is highly relevant for machine learning research because it concerns the factors that determine the subjective difficulty of concepts. For example, why are some concepts psychologically extremely simple and easy to learn, as we have seen before, and while others seem to be extremely difficult, complex, or even incoherent? Look, for example, in your field, you look into the medical domain. And these questions have been studied since the 1960s, but are still unanswered. So just that I have mentioned this. So a few certainties: the baby does not know what Google is, but the baby does also not know what a banana is. So we will see this in the next lecture. So how strong is the relationship, or does a relationship exist? So this is the question of cognition as probabilistic inference, where we use our visual perception, the language acquisition, motor learning, for example, associative learning, memory, attention, categorization, reasoning, causal inference, decision-making, theory of mind. All of this is of complete difficulty for modern artificial intelligence and machine learning. So learning concepts from examples is a big goal, and learning and applying intuitive theories. So this is this balance and trade-off of complexity versus the fit. And this brings us to modeling basic cognitive capacities as intuitive Bayes. So this is also a work from Tannenbaum. So the theory-based Bayesian framework provides for us now a formal means to address several fundamental questions about human cognition. For example, what is the content and form of human knowledge? At multiple levels of abstraction, how can abstract domain knowledge guide the learning of new concepts, and how can abstract domain knowledge be learned? And what conceptual resources must be built in? Is this innately? Is this learned afterwards? How do mechanisms of statistical learning and inference interact with and operate over our structured symbolic knowledge? So this is very important because traditionally computational approaches accounts that aim to explain a broad spectrum of human cognition, and they have focused exclusively on either sophisticated inference process or sophisticated knowledge representations. So this is similarity, for example, or representativeness and evidential support, causal judgment, coincidences and causal discovery, diagnostic inference, and of course predicting the future. This is exactly what is the goal of medical artificial intelligence, medical AI, machine learning. This is the topic of our course. Yeah, and this let us now go even more back into the past. You know, if you want to look into the future, the best is to look into the past to understand the past. So how does the short-term sensory or the long-term short-term storage or long-term storage model work? So this is an oversimplified model, in particular when it suggests that both short-term and long-term memory or storage, as they call it here, operate in a single uniform fashion. We know already, or meanwhile, that this is not the case. So please disregard now the incompleteness of this model, but it is a good approach to understand information process as the core of research in decision support. And also this brings us a little bit closer to cognitive performance. So, and yeah, I have really here to mention that we have dozens of different models available in the scientific community, and here this is just one single one, maybe the most prominent one, but this is the famous 3-storage memory system developed by Atkinson and Shiffrin in 1971. So let us look closer at this model. So you have this environmental input from the outside world. So this is the stimuli from outside. Then you have your sensory registers, for example, the eyes, the ears, your touch system, so visual, auditory, and so on, the sensory registers. And then you have this famous short-term storage or short-term memory. I say short-term memory or working memory, temporary working memory. And here you have all these control processes of rehearsal, coding, decisions, retrieval, and strategies, and so on. And now we have a certain response output. So you immediately process, sensor the stimuli from outside, and you can immediately respond on this via your control processes in the short-term sensory on a short time. And then you have, of course, this permanent memory store, this long-term storage. And from there you have the knowledge. So you build the knowledge of your world. So concluding, we can say that it is of importance to have a model of the user's knowledge, allowing now to measure the differences between what is short and what is long. So while this information, these basic sensory registers take this information, keep it in the short-term storage, the information in the long-term storage is associated with much more, let's say, encoded knowledge. But I think this will be much clearer if we look at the next slide. So this is the original slide from 1971, but the next slide will be easier for you. So this is the general model of human information processing after Wickens 2004. Here you see the several steps. So for example, you have the physics here, the sensory processing, then you have the perception, then you have the cognition part, and then you have the motorics part as an output. And as ultima, we can immediately go to back to our first slides, which we have learned in the first part of this course. So you have data and you have hypothesis. So if I go back one slide, so you have data, incoming data into this sensory processing system. You perceive this data and now you build hypothesis. So you build hypothesis in your taking from your long-term memory, and now you check the hypothesis with your data. And this is very similar as we have learned with Bayes, with the basics from Laplace. So for example, you have a prior probability, then you have the likelihood that this is true, and then you have a posterior probability, and this is now ongoing. And as you know, for the sake of completeness, in the medical domain, we have always to marginalize this, so to divide it by this division, so to make it, for example, as an correct output. And this is the connection now between decision making and cognitive science. So this is really very, very good. Human decision making is perception and response execution. This is an outcome, and this is an activity tied to, for example, fallibility, especially in complex and dynamic situations. But let us look how it works. So for example, we have here this nebula of uncertainty, you have here the physical stimuli, you have here your selective attention. This is the set of your incoming data. We select this, what is interesting, what is relevant, we pre-select this data, and we form and we compare. We form now a hypothesis, and we compare this hypothesis, the theta parameters, from your long-term memory, which is your previous set knowledge. And now we have the choice, the decision making. So we compare and select the best possible choice as an answer to the working hypothesis, and this triggers then an action. And the outcome is then feedbacked, but also to this nebula of uncertainty. So always prone to this selective attention here, this selective attention mechanism, and then the same goes on, and this is exactly what happens here. So you always start with the prior, you have a certain likelihood for the prior, and you get out the posterior probability for this that the hypothesis is true, and this is ongoing, because you have always this feedback loop. So, and you see, this is very close to how our machine learning algorithms work. Therefore, this is so important to understand that. Okay, this brings us now really to probabilistic decision making, so how to make decisions in a domain of uncertainty. And here again, Pierre-Simon de Laplace, 1812, it is remarkable that a science which began with the consideration of games of chance should have become the most important object of human knowledge. This is really very, very nice, a very nice statement. So what is signal detection theory then doing? So here you see the early beginnings here on the radar screen, and here you see you have a hit if you detect, for example, an incoming aeroplane, and you have a correct rejection, for example, if you don't spot it. So if it, for example, is a cloud from a weather. So you have here noise, you have then signal noise, and then you have let's say an distance between signal and noise. And this is then the decision variable. So you have the noise distribution and the signal distribution, and you have always this signal likelihood and the noise likelihood. And the goal is to find out. So ideally, this would be overlapping. So ideally, of course, you would make no errors. But this is only in the ideal world without noise. But in the ideal world, you have always noise. Practically, you have signal and noise. Okay, so how is this applied in medicine? So you see here two doctors, so Dr. A and Dr. B, they are equally good in training, looking at the same CT scan. So both will have the complete same information, but they may gain different knowledge out of the data due to many intervening factors. They can be biased, of course, they can have different criteria. So interpreting CT data is difficult and it takes a lot of training, and there's always some uncertainty as to what is correct or what is not correct. So in principle, we have now exactly four possibilities. Let us look at this. So either there is a tumor present, so hit tumor is present. This is case A. Tumor is present and the doctor says yes, correct. And we have correct rejection. This would be then the opposite case. So tumor is absent and the doctor says correctly no. So, and then unfortunately we have a case here, miss, the tumor is present and the doctor says no. And then of course the case that of a false alarm, so the tumor is absent and the doctor says yes. It's also so dramatic. And this is really a difficult problem. So here hit tumor present, the doctor says yes. Correct rejection, tumor, no tumor, doctor says no. And then we have this false alarm and then we have this miss. Okay, so how do we measure now the quality in this signal detection theory? So with this table, this is a contingency table, and we will see later on how this is used in artificial intelligence and machine learning. So we have this green, this is hit and correct rejection, and then we have this miss and false alarm. And this now can be depicted by this probability Gaussian distribution. So distribution when the tumor is present, distribution of internal response when no tumor is present. And then you have the internal response. This is depending then on the decision maker. And here you can have an internal response of that kind. So this is the criterion response. Then you have a hit and a miss probability. And then you have a correct rejection and a false alarm possibility. So this is the possibility of the four criteria here. And this is actually a very, very, let's say, basic term. So this was long time in use before even machine learning was there. So in signal detection theory, we speak about this receiver operating characteristic, the famous ROC curve. And this is the curve which illustrates the performance of, for example, a binary classifier. So in here, and this is a typical case. So we have, for example, here a case of t is equals to 0. So this is complete random. So the outcome would be complete random. And then we get better. So the ideal case would be a complete here, an edge here without any bending. So the area here is a direct measurement for performance, as we will see in the next slide. So here we go back to the famous paper we have seen in part 1 of our course. You can remember this is the famous paper from retinopathy. And here you see this receiver operating characteristic curves. Let us look at the large one. So here we have the false alarm rate on the X scale, and on the Y scale we have the hit rate, so hit versus false alarm. And here then you have this blue line, and this blue line is the performance of the algorithm, you see, and these dots are the performance of the human participants in this study, and you see here the human are close on this line, but here the humans are not as good, and we can now zoom in. So we zoom in now, you see this is 100%, this is 0%, 100%, 75%, and now you see that they are close on this border, but what you see is that the algorithm also is not perfect, and most of all the algorithm has some, let's say here, some gap also, and we are far away from 100%. So ideally the performance would be completely super if we would have a curve that goes up, straight up here and straight down here, okay? But it's not the case. So basically we have this receiver operating characteristic, this ROC curve, as a measurement for the performance of an algorithm, and more precise we can measure the area, or we can calculate the area under the curve. So the area under the curve is a direct measurement for the success of performance. So we are now really talking about pure performance measurements, okay? And this is the performance measurement ideally is 1 if the area is 1, and it is completely random if, for example, it is 0.5, okay? So next we will see the confusion matrix, or earlier called contingency matrix. So in the field of machine learning, and this came out of the problem of statistical classification, a confusion matrix, and formerly it was also known as error matrix, is a specific table layout. Here we see it, the table layout. And this allows a visualization of the performance of an algorithm with the numbers in it. For example, here you have a pre-training. This is the pre-training from our retinopathy paper. And you see here, we still have in the first round an error rate of 46%. And with this confusion matrix, I can see where the errors are. Okay, this is very important. So you see, the darker the blue is, the better the performance. So ideally, only in this diagonal would be the numbers. Okay, but you see routine, we have 33 hits here and 21 here. So in the next round, after the next training, we see it's much better. We have only an error rate of 3.4%, and we see here and here we have still some outliers, and here it is not so good, but here is the best performance, you see. So this is so technically each row of this matrix represents the instances in a predicted class, while the column, or each column, represents the instances in an actual class, or vice versa. So it depends on the naming of the axis. So, and the name, this stems from the fact that it makes it easy to see if the system is confusing two classes, so commonly mislabeling as one as another. So this can have many dimensions, of course. It can be binary, then it has only 4 tables, as we have seen before. And here we have 1, 2, 3, 4 rows and 4 columns, okay? So this is a good example. And out of this, now you can form the measurements, so the accuracy, the misclassification rate, so overall how often the algorithm is wrong, or the true positive rate when it's actually yes, how often does it predict yes, or the false positive rate when it's actually no, how often does it predict. So, and true negative rate and precision when it predicts yes, how often is it correct. And of course the prevalence, so how often does the yes condition actually occur in our sample. You see, so you can quantitatively judge the quality of your algorithm, of your medical AI or machine learning algorithm. Okay, so for your information, so this slide is just additional information. I skip this for now because you can read this on your own. And also this is just for your information. So this is a comparison of decision-making process with data mining process. And here, just for repetition, you have again that you see, this is really very important, that this model can describe this hypothesis and the probability of the hypothesis given the data and so on. And this is basically machine learning, as we have seen in the first part. The posterior is the likelihood times the prior through the evidence. And the evidence, this is what I have mentioned before, the evidence is this marginal likelihood. This is called normalization. And why do we normalize? That we have some numbers which we can understand. Because what does 10,622 mean? You don't know it. But I can show you between 0 and 1, and then you know 1 is the best and 0 is the worst, and then you see 0.89 is a very good quality. So therefore we need this normalization. And this can be tricky. This division can be very tricky. This dividing through the evidence is a very tricky part of our whole machine learning process. So remember, the inverse probability allows to infer these unknowns, learn from data and make these predictions. And this is the grand goal of machine learning, to make predictions, to look into the future. So learning from examples and to look and to prospect into the future. And this you do on your daily basis. For example, when you apply Bayes rule for medical diagnosis. So this is a standard example, schematic representation of these Bayes rules on these smallpox symptoms. So the data are in the form of symptoms. Yeah, they are used to find a likelihood, and which is then the probability of those symptoms given that the patient has a specific disease, for example. And this Bayes rule combines this likelihood with prior knowledge, as we have seen before, and yields then the posterior probability that the patient has the disease given that he or she has the symptoms observed. So you see again, this is the posterior, the probability, the likelihood, and of course you do also this evidence, this marginalization. So this is a beautiful example how close you as in the medical domain are to medical AI or machine learning or decision making. So you are kind of a machine learning algorithm too sometimes. So this is then a little bit trickier. So comparing the probability of chickenpox and smallpox. So this is a big difference, as you know. So you use here Bayesian inference. So the observed symptoms seem to be more consistent. So with smallpox, chickenpox, and so on. However, the background rate of chickenpox in the population is higher, as we know, than that of smallpox, which is in this case, then it makes more probable that the patient has chickenpox, as indicated by its higher posterior probability. And this you can infer into this model, and then you have this Bayesian inference for this more complex case. Yeah, and by the way, this was a case which was diagnosed in 1977. So this was also it was in the time where artificial intelligence was used already. So a final practical example let's say to cover this we say it in German, Alltagsmissverständnisse von bedingten Wahrscheinlichkeiten. So in other words, if you have a disease, it shows you with 99% probability and you don't have the disease, it shows that you do not have this and so on. But I will show it step by step that you understand the basic reason. Okay, so your medical doctor, this is this guy, has bad news and good news for you. Bad news first, you are tested positive for a serious disease, hopefully not COVID, and the test is 99% accurate if you are infected, okay? And we determine this case as T, hard T, okay? Capital letter T. Good news, it is a rare disease striking only 1 in 10,000. This is the letter D, delta. How worried would you now be? So this is the fact. So again, bad news, 99% accurate if you are infected, and I emphasize if you are infected, okay? And good news, striking 1 in 1,000. Okay, let it now check. This is exactly this rule. Posterior is the likelihood times the prior through the evidence. So how does it work? So we have the probability of the hypothesis given the disease equals to the probability of the data given the hypothesis times the likelihood through the evidence, okay? So now we set in our numbers. So P of T is 1, binary, and D is 1, is P of D of H is, now you can calculate this, 0.99. And P of the P is the Wahrscheinlichkeit of, so P, the probability of D is 1, and this equals to P of H. This is the hypothesis now, this is this term, is 0.001, okay? And now you set it into this formula, likelihood prior evidence, and you get out a final posterior with 0.0098, so it's very little. So you can relax. It is not so likely that you are infected. Okay, so precision medicine, personalized, predictive, preventive. This is the further examples, but I will skip this briefly because we are running out of time. So you are looking for the coffee already, of course. But let us quickly go through these examples. So this is an example from exon arrays. So this progress in genomics is enormously increasing, and this also raises the data available for conducting expression analysis. This is used in transcriptomics, and this is good. This can be very helpful for decision support, and you know, big data is good for machine learning. So this is an ideal case for using machine learning. And this is an early example, and I show you this computational leukemia cancer detection. This was one of the first works by Corrado et al. So this is in hybrid systems, including 3 experts in sequential order. So you have here humans in the loop and integrating completely different techniques. So you see this is the pre-processing here. Then you have pre-processing and filtering, then you have the clustering here, then you have the extraction of knowledge in these decision trees as we have learned before, and then you have this information representation in terms of visualizations. So this is an expert process, and then you get a decision support, and we will now look into more details. So for example, this slide shows now the classification performed from patients from different groups. For example, the CLL group is cancer characterized by proliferation of lymphocytes, or for example, this all is cancer of blood and bone marrow caused by an abnormal proliferation of lymphocytes. So the classification is now obtained for all patients and for the CLL patients. And each of the values obtained correspond now to the fluorescence intensity for an individual. And at the bottom of the image it is shown the fluorescence scale of values. The lowest level is 2. And this is blue, while the highest is 12. This is red here. Yeah, and for the interpretation of these images in color, you can refer to the original article by Corrado in more detail. So I just want to show that this is also using a decision tree. So you see how important the decision tree is. So in this slide, the patients were assigned to the expected groups, and only one of the patients was assigned to a different group by both methods. And the healthy patients were eliminated in order to proceed with the classification. So this tree helps actually to obtain an explanation of the reason why an individual has been assigned to a group. So you see, for explainable AI, decision trees are quite a good tool of the trade, although you see this was used in 1984. So this is quite a long time ago. Okay, this Corrado has visualized this in a three-dimensional space. So you combine now methods to reduce the dimensionality of the original set of data. This is, of course, dangerous because you can lose information, as you, of course, will understand. Then you have the pre-processing and the data filtering techniques. Then you have the clustering method, and now you have the extraction of this knowledge and to visualize this in this scatter plot in the 3 dimensions. And what should we or what can we now learn from this model? So they combine methods to reduce the dimensionality of the original data set. This is actually a very difficult task. Then they do pre-processing and data filtering techniques to raise the quality of the data, for example, and then a clustering method to classify the patients, and then to do extraction of knowledge techniques. And finally, they visualize it. And this system reflects how human experts work in the lab, but also this is in real action, and therefore I'm showing it to you. This reduces the time for making prediction and reduces the rate of human error. And this works with high-dimensional data from action areas where humans cannot see anything because it's too high-dimensional, so it's too complex. So here a computer, I call it artificial intelligence. Here the artificial intelligence is really very helpful. So next example and final example, and then you are ready for the coffee. So case-based reasoning, this is a problem-solving paradigm. You know this from different other AI approaches. So instead of relying solely on general knowledge of a problem domain or making associations along generalized relationships between problem description and conclusion, with this case-based reasoning, you are able to utilize your specific knowledge of previously experienced concrete problem situations. These problem situations are called cases and therefore case-based reasoning. So thinking, reasoning, deciding, acting. Always remember that thinking, reasoning, decision, action is intrinsically tied together. A good primer for clinical thinking is the book here by this Gambrill, and I would really recommend if you look this up in your spare time. Another is this Rosalinda Alfarelli. This is a classic reading. Okay, case-based reasoning goes back to the early times. So case-based reasoning is a problem-solving paradigm, as we have heard before. So how does it work? A new problem is solved by finding a similar past case. So you start here with the new case, yeah. You retrieve now similar cases from your previous cases from your database. And now you reuse this and you put this then as a learned case into your previous cases. You should constantly learn again and again. So this is constantly learning, and therefore you can retain it for future use. And this case base is always updated with new learned case, and you can of course modify some existing cases. So this is long time in use and is still state of the art. And you see this is a paper from 1994, and this was published in Artificial Intelligence Communications in 1994. Very good example. Yeah, in this slide we see again the task method structure. Tasks have node names in bold letters, which, for example, are the case tasks, and the methods therefore are written in italics. Okay. And the links between the task nodes, these are the plain lines, are task decompositions, for example, part-of relations, where the direction of the relationship is downwards, as we can see. So the top-level task is problem-solving and learning from experience, and the method to accomplish the task is case-based reasoning. So this is now a good example. And this can also be very complex, and the challenge is to make it understandable for the human. And this is actually a grand goal now in what is now called explainable AI. Okay, so radiotherapy planning, the last example. So for cancer treatment, this is a computational complex problem. And for example, here prostate cancer is generally treated in 2 phases. In phase 1, both the prostate and the surrounding area where the cancer spread to will be irradiated, while in the phase 2 only the prostate will be irradiated. And the total dose prescribed by the oncologist is usually in the range between 70 and 76 gray, while the dose ranges in phase 1 and 2 of the treatment are somehow smaller. And the dose is very, very important because, as you know, this can can cause damage. Okay, so here you see the typical workflow: CT scanning, tumor localization, skin reference marks, treatment planning, virtual simulation, radiotherapy treatment. Now, how can AI assist here? So here again, case-based reasoning. So the generated scans are passed onto the planning department. In the planning department, the tumor volume and the organs at risk are outlined by a medical physicist, and so that the region that contains a tumor can be distinguished from other parts. So this is the most critical part. And then you have measures, for example, a clinical stage labeling system, the Gleason Score. I will come to this in the next slide. And the prostate-specific antigen PSA value between 1 to 40. And then you have this dose volume histogram. So this is also a value between one of these percentages. So this works now in this system. The cases which are similar to the new case are retrieved using a fuzzy similarity method. And this is called modified Tempster-Schafer theory. And this is applied to fuse the information from the retrieved cases together and to generate a solution as shown in the slide. But we do not focus now in this detail. I just show you how this fuzzy sets work. So the Gleason score, this is very well known. These are samples from the prostate biopsy, and together with other parameters, it is incorporated into a strategy of prostate cancer staging with the staging, and this staging predicts the prognosis and helps to guide therapy. Gleason score is given to prostate cancer based upon its microscopic appearance. As you know, cancers with a higher Gleason score are more aggressive, of course, and have a worse prognosis. So you can see this here, and now we have this application of fuzzy logic. You see, this is not binary, but it has some borders here. So the parameters in these membership functions are set in collaboration with the oncologist, and this is a good example for such an human intervention. So in the final slide, we demonstrate the adaptation mechanism. So in this example, the final outcome is a dose plan. And this dose plan, as you can see here, this is this 62 grays plus 8 grays. And this dose correspond to the phase 2 of the treatment. And this is a tricky part. And therefore, it's really, really important that here the medical doctors get help from the artificial intelligence at this time. Okay, conclusion. So, problem solving, humans versus computers. So, when is the human better? So, when human is better, what is human? We speak about human intelligence, but we don't know what intelligence is, I know. So maybe we talk about natural intelligence or human mind, human brain, learning, whatever, I don't know. So where is the human better? Natural language translation creation? Not quite, because if you look at DeepL, the natural language translation is actually on or beyond human level, even beyond human level. So in certain cases, you need an expert, for example, for very tricky parts of text. So, but what is true, computers cannot understand the context of sentences. Humans are good in unstructured problem solving. Without a preset of rules, a machine has trouble solving problems because it lacks the creativity required for it. Then we have a lot of NP-hard problems, as we have seen in part 1 of the course. And processing times are often exponential and makes it almost impossible to use machines for it. But humans make heuristic decisions which are often not perfect, but, and this is the point, sufficiently good. Okay, when is the computer better? So the computational intelligence, artificial intelligence, soft computing, machine learning, however you call it. So whenever high-dimensional data is the case, and this is in the medical domain often the case, yeah, then humans are very good at dimensions less or equal than 3, but computers can process data in arbitrarily high-dimensional spaces. Then computers are better in rule-based environments, so difficulties for humans in rule-based environments often come from not recognizing the correct goal in order to select the correct procedure or a set of rules. So there the humans are not so good. Then image optimizations, a machine can look at each pixel and apply changes without human personal biases and with more speed. Although this is not quite correct because we know, as we have learned in the past, also computers can be biased. This is naturally because if you have imbalanced data and you train from a certain data source, then the algorithm is biased. So this is also a problem with machines. So it's the slide is a little bit older and is not quite on the state. And now, speaking about old slides, I show you now a very old slide. So this is more than 20 years ago. This is a very old table from my early works, maybe helpful for you at the first glance, but please excuse for the crudeness and the simplicity of this work. This was the very first steps. Okay, conclusion. Computers are incredibly fast, accurate, and stupid. Humans are incredibly slow, inaccurate, but brilliant. Together they are powerful beyond imagination. So this would be the typical human, let's say human-centered AI approach. This is attributed to Albert Einstein, but we know from some research what Ben Schomer did, Einstein never said that because Einstein surely had no computers at this time. Okay, ladies and gentlemen, with these words I close part 3 of our course Medical Artificial Intelligence. So I thank you, and now please enjoy your coffee. You have deserved it. Thank you very much.